the first slide, right? Okay. Okay, chapter 2, Introduction to Engineering Materials and Their Properties, right? Okay, we know that materials are essentials for a design. Okay, so in this chapter, uh, we will be introduced to various type of materials that engineers can choose. Okay, and we also would like to see how the properties of the material will impact the performance of product. Okay, so engineering materials can be grouped into 6 main families, as you can see in this slide. Okay, we have metals, polymer, elastomer, right? Elastomer is basically this is a rubber-like materials, and we also have ceramics, glasses, and hybrid materials. All right. So, what does it mean by hybrid materials? Okay, this group of materials is actually combining two or more type of materials, right? For example, we have a composite. So each family has certain features in common. Okay, for example, like how they are processed and how they will be used. Okay, for example, metal. Okay, we know metals. Metals are strong. Metals can conduct electricity, while ceramics. Okay, ceramics. Ceramics are heat resistant. Ceramics are hard, but remember, ceramics are brittle. What is brittle? Anyone? If you still remember engineering materials, you learn about the properties. So what is brittle? Sorry?
Rapuh.
Yes, rapuh. Okay, brittles can break easily, right? Okay, materials information for design. So engineers usually, okay, or often use materials that they already know, okay, the material that they trust, because there's a lot of reliable data available on that particular material. So this means they know how exactly the material will perform, okay, so that there will be less risk involved when using the materials in their products, okay, or in a structure. Okay, for example, okay, we have aluminium. All right, aluminium is a well-known material that been used in aircraft construction. Why? Because this aluminium is strong and durable, right? So therefore, engineers they got a lot of data, okay, data on this aluminium properties, okay. Uh, so they know how much weight this aluminium can hold before it breaks, okay. Mm, Basically, they know what is the strength of this aluminium, okay, and how this aluminium will behave in extreme temperatures, okay, for example. But then we have this carbon fiber, all right. Carbon fiber composite is the newer materials that is much more lighter, okay, much more stronger as compared to the aluminium. uh, and some more, this carbon fiber also uh, been used in the sport cars, in the bicycles. Why? Because uh, by using this material, it helps to improve the speed and also the efficiency of those cars and bicycles. Okay. However, okay, early version of this carbon fiber had actually faced some problems lah, like um, the brittleness, all right, the brittleness of the carbon fiber itself, okay, and also the costing, okay, the cost for the carbon fiber is quite high. So over the time, the engineers will gather more data, okay, so uh, this data is coming from the testing, of course, and from the data they investigate and make the carbon fiber more safe, more safer, and eventually it is more reliable. Okay, so now we see this carbon fiber has been used in many cutting edge applications lah, such as in the aerospace industry, and also apa, Formula One punya racing car, right? Types of materials information, right? If you're going to design something, uh, what sorts of material information that you do, all right? Uh, okay, all right. So what do we have here? We can see here the tests that been done. Okay, from these tests we have the raw data, right? The raw data uh, been collected from the test. Okay. However, okay, whatever number that are coming from the test, okay, the result from the test uh, is what we can say is not useful for us yet, right? We need to conduct the statistical confidence to make the data more meaningful. Okay, okay. Actually, all these material tags is uh, all those material data are typically been presented in terms in form of material text, right? So, and we also have the engineering handbooks, right? So in the engineering handbooks, they present the test data with the value of allowables, right? So material information that need for design. Right. So we have a mean value. Okay, from the test data, they calculate the mean value of the property when measured on a large batch of samples, right? And then they also determine the standard deviation of the measurement beside the allowables. Okay, so allowables is actually the property values that can be guaranteed with a certain level of confidence, so that the data becoming more meaningful, right? So this raw data and the statistical confidence uh, is then we can use to proceed with the design process. Okay. Okay. As I mentioned earlier, okay, they are material tags. Okay. That's presenting the test results, right? And we also have engineering handbooks that include the safe limits or known as allowables, right? So when the data is accurate, okay,
Doctor,
yeah,
may I go to toilet?
it's up to you, right? You
Thank
may
you.
go if you want. All right, when the data is accurate and reliable, it becomes useful information. So this data is actually being organized in a table like this. Sometimes in form of yes, no answer or ranking. So why? Because to make it easy to understand, to compare, right? So many attributes can be structured, are common to all material. For instance, having density, okay? Most of the material are having density, elastic modulus, strength, and as well as thermal conductivity. Okay, what does it mean by the density of a materials? Anyone? How about the density of the material? What does it mean? Okay, density is yeah, density is actually referring to how heavy it is. So when we want to know whether uh, the material is heavy or not, we always refer to the density. We compare the density. How about the elastic modulus? What does it means? Elastic modulus. Elastic modulus is referring to flexibility, right? And thermal conductivity. Okay, okay. What is thermal conductivity? What
Heat
does
conductivity.
Yes, exactly. It's referring to how well the material will conduct heat, right? So this structure can be stored in database, and because all materials have these properties, so it is a foundation for choosing the right material for the structure, right? Okay, so what we can say to design a materials, you need to know its real character, which means its strength and also its weakness. Okay, so how are you going to shape it? How you're going to join it? Who has used it before and for what? Uh, did it fall? Did it fail? And why it failed? uh, what are the damage mode that potential to that kind of material. So all this information has been documented in the handbooks as a design guideline. Okay, in that handbooks, there's also failure analysis and also case studies, right? Okay, materials used are subjected to standards and code. These rarely refer to a single material, but to classes or subclasses, right? To succeed and be profitable in the marketplace, a product must be economically viable and compete successfully with the competition in terms of performance, consumer appeal, and cost. All these depend on the material choice and the way the material is being processed, right? Right. So now we move into material properties and their unit. All right. So we know that every material has a unique set of properties. Okay, what does it mean by properties? Okay, the properties is referring to like how strong it is. Okay, how much it can stretch before it break. Okay, uh, those are the properties of a material, right? So these all these properties have been measured, and also the properties has been organized into we can say a profile for each materials. Okay, so this profile will help the engineers to decide which material to use, okay, for a certain structure. For example, right, engineers may look at how dense a material is, right, and how well it will conduct heat, right? So the properties are measured. Those properties were measured using the standard unit. All right. Uh, Typically, we use the SI unit. What is SI unit? What are the examples that you know? Okay. Example for SI units are like meter, kilogram, right? So that it is a standard. Okay. Okay. These are the general properties. All right. We have this is density, right? Uh, Density is actually the amount of mass that of a material that has in a given volume. Basically, it is how heavy something feel for its size. Okay, for example here. Okay, we have a block of steel. Uh, okay, this steel is much heavier as compared to this block of wood, even though they have the same size. Why? Because the steel is having higher density. Okay, so density is actually a physical property. Okay, which uh, which uh, which is a general property. So it does not relate to how material behave under a force. Okay, so if that will go into mechanical properties. But these general properties, okay, this density is actually describing a basic characteristic for a certain material. Okay. Next, we have price. Okay, price. Okay, we all know that price is referring to how much the material costs, okay, or how much it costs to buy or produce a material, right? Okay, so some materials like gold are very expensive, while the others like plastics are much more cheaper. So price is not a physical or mechanical property. Instead, it is an what we can say it is economic or commercial property. Okay. Even though the price of a property can change, we should have a rough estimation for a material cost. Why? Because it's really helpful when you are just starting to choose which material to use for a project. You still need to consider the costing, right? Price does not describe how the material behaving in a scientific sense, but however, this price ni as a property is important in material selection process. So to conclude this, okay, density will tells you how heavy a material feels for its size, and we have price. Price are telling you how much money the material will cost you, right? Okay. So this is the table that lists different mechanical properties of a material, right? So just now we look at general properties, and this is mechanical properties, right? So these mechanical properties are actually the characteristic uh, for a materials that are telling us how a material will react, okay, how the material will behave when the forces are applied to it. We give the force to the material and how it will react, okay. uh, in a simple terms, these properties describing how strong, okay, how tough, and how flexible the materials. When you push the material, or you pull, or you bend, or even you squeeze it, okay, so you have those characteristics. So why we need to know these mechanical properties? Okay, because we want to understand how the material will behave when we use to build something. Okay, okay. I take example. The strength. Okay, the strength properties. Okay, we have here the strength. Several type of strength. We have uh, tensile strength, compressive strength, failure strength, right? So this strength actually telling us how much uh, the force that a material can handle before it breaks, okay, before it reach its breaking point. So how much the force that material can handle or can endure that amount of stress, okay. We also have apa lagi? Flexibility. Alright, flexibility. Okay, you might see through elastic modulus, alright, or ductility. So these properties will actually telling us how much the material can be stretched, okay. So we can see we have the flexibility property. So how much the material can stretch or bend, okay, without snapping, okay, without patah. Okay, for example, we have mm, a metal wire, right? A wire made of metal. Okay, so we can stretch it into a long, thin shapes. Okay, why? Because the behavior of the material itself, it is ductile, right? Okay, another example is hardness, right? Hardness. We have hardness. Hardness telling us how resistant it is, um, resistant to being scratched, okay, or dented, right? So these properties, okay, all these properties are super important, okay, as okay for us to design things like a bridge or airplanes, or even if we want to design a simple chair, okay, because it will help you as the engineers to choose the right materials that will not break or will not bend under any given pressure, right? Okay. Okay, so today again we're going to look into chapter 2, but we will cover the part that we did not manage to look last week, right? Okay, general properties dan mechanical properties. Yes. Okay, so we are going to continue on this stress strain curve, right? So the figure that you see here is actually the stress versus strain curve. Okay, so this curve is actually being used to describe how a material behave when it's been stretched or when this material been pulled under this tensile loading. So basically, it will help the engineers to understand how much force material can handle before it start to deform or break, right? Okay, so we know that the stress is the force that been applied to a material and divided by the A. What is A naught? What is A naught here? A naught here is actually referring to the area that the force been applied, right? The cross section area. So it is basically the stress ni is like how much pressure did you put on the material, okay? And on the x-axis we have here the strain, right? The strain. This is strain. Strain is actually the amount of the materials that been stretched, okay, delta L, and we compare to its original length, L, okay, L. This is the original length. So this strain will actually tell you how much the material deform, okay. All right. If we look at this curve, this stress strain curve, okay, so we will see the initial straight part here, okay. So at this straight region, all right, is showing the elastic behavior of the material, right? So what happened in this region? Um, if you remove this force, right? So the materials, okay, these materials, when you remove this tensile force, the material will return to its original shape, right? So as for example, if you stretch the rubber band, okay, getah, um, getah, the orange getah that we get when we go to the shop, right? Or when we go to the market, right? So it has the ability to stretch and it will turn back to its original shape when we remove the force, right? So if you look at this elastic region, there is a slope, right? Slope. This slope for this straight line is called Young modulus, okay, or elastic modulus E. Okay. So what does this elastic modulus measure? Anyone? What does this E measuring?
Stress over strain.
Yes, but what does it represent? Stress over strain. What does it represent? Okay, this Young modulus is actually measuring the stiffness, all right, the stiffness of the material. So, a steeper slope means that it is a stiffer material, right? More steep, the material becoming more stiff, right? Okay, then if we go through this line, right, we found a point where the curve start to bend. Okay, after the straight line, the curve is start to bend. So this point is called yield point. Okay, so at this yield point, we have yield strength, right? So this yield strength is actually stress at which the material begins to deform permanently, right? It start to deform permanently. Tadi elastic region, it start to the materials when we unload the material, it will go back to its original shape. But when it reach this point, the material will deform permanently. Okay. After what does it mean? Uh, After the material reach this point, it won't go back to its original shape. If we remove the forces, even if we remove the forces, it will not go back to its original shape, right? All right. Next, we have the highest point of this curve, all right, here is called tensile strength. Okay, tensile strength. So this is the point where we obtain the tensile strength of this material. Sometimes in the textbook, you might also encounter the terms ultimate strength, right? So this is actually the maximum stress the material can handle before it start to weaken, right? So after reaching this point, the material is about to break, right? So after this tensile strength, if we notice, this curve is started to drop. Okay, so which mean in this region, okay, the material is started to weakening, material to semakin lemah. So the point here, okay, if you can see the point here marked with an asterisk, okay, is the point where the material breaks, or we can say the material fail, right? All right. So what else do we have here? Okay, we have 0.2% offset, right? So what does it mean? What does this point mean? Okay, why do we need this 0.2% offset? So what does it mean? So the point, okay, or this line is 0.2% offset from the original, right? So okay, so how why we need this line? Because we want to measure the yield strength of the materials. All right, so sometimes the material does not have a clear yield point, so we set to be 0.2% offset from this originate, right? So it is actually a method of drawing a line parallel to this elastic region, right? And it will intersect the curve, okay, intersect this curve, so that we can obtain the yield strength, right? Okay. So here are the important parameters related to stress strain curve, right? We have elastic modulus or Young modulus, all right? E, the unit is gigapascal or giganewton or per meter square. So what does this parameter do? So it measures the stiffness of the materials, either in tension or compression loading, right? And we also have shear modulus, okay? G, the unit is same as the Young modulus, right? Gigapascal or giganewton per meter squared. So this shear modulus is actually measuring the stiffness due to shear loading, right? For elastic modulus or Young modulus, okay, the stiffness we measure is under tensile or compression loading. And for stiffness under shear loading, we have shear modulus. Okay. We also have this bulk modulus, okay, where it responds to hydrostatic pressure. Okay. On the top of that, we have Poisson ratio. Okay. Poisson ratio is actually negative of the ratio of the lateral strain. Okay. The strain in the lateral direction. What is this sign? What is the symbol? Lupa dah. Alright. Okay.
Gamma.
No, this is not gamma. This is what is this?
Epsilon.
Epsilon. I should epsilon. Okay. Epsilon 2 over epsilon 1 is a negative sign. So this is the Poisson ratio. So all these are the important properties of a material, right? Okay, all right. So this is the relation of moduli for the isotropic materials, right? From E, all right. How to obtain the Young modulus? Okay, we can obtain Young modulus as a function of this shear modulus and bulk modulus, right? For shear modulus, okay, shear modulus is a function of Young modulus and also Poisson ratio. If we know the Young modulus of the materials, right, the Young modulus is the stiffness under tensile and compressive loading, and if we know the Poisson ratio of the material, we can calculate the shear modulus for that particular materials, right? Okay. Same goes to the
bulk modulus. Right? So we need to know the Young modulus and the Poisson ratio. Okay. So I just want to emphasize about Young modulus, right? So this Young modulus again is a fundamental property that indicates how much materials will deform elastically. Okay, elastically, because it is in the elastic region, right? So the higher Young modulus, okay, the higher value of Young modulus, meaning that the stiffer material is, okay, which means, okay, it will experience less elastic deformation, okay, under the same load, okay, as if we compare to a material with a lower Young modulus value. Okay, so and shear modulus is important for us to understand the material behavior under torsional, right? Torsional or shear loading, and also it gives an idea on the how easily it can be deformed in direction parallel, right? Parallel to the applied force. Okay, so if you look at this figure, right? The material here, okay, is being loading perpendicular to the uh, to the specimen, right? To the specimen. So here the loading is parallel to the specimen. Okay. Right. Young modulus, okay, for copper is 1 to 5 gigapascal, and Poisson ratio is 0.345. What is the shear modulus for the materials? All right. Can you guys, okay, take your calculator and calculate for me? All right. We know the Young modulus, 1 to 5 gigapascal, and we also know the value of Poisson ratio, 0.345. All right. So we would like to know what is the value of shear modulus. So what are we going to do? All right. We're going to use this relation of moduli, okay, to obtain the value of shear modulus when the value of Young modulus and also Poisson ratio is given. Okay, anyone got the answer?
Doktor nak tanya, nanti dalam exam ada formula?
It depends. Kalau formula yang simple formula, alright, like sigma F over A, this one is not being given, okay? For this one, yes, it might be given, alright? Ni macam stress, F over A ni, force over the cross-section area. This one you should know, okay? You should know like you know back of your hand, right? And the strain, how to calculate strain, this definition of stiffness, okay? So you should know all these simple terms, right? So is there any answer for the question? Come on. Come on, tidak lagi kah? Sorry?
46 gigapascal.
Okay, okay, 46 gigapascal, right? 46.1 gigapascal, right? It's straightforward. Just substitute the value in the equation and you get the answer, right? Okay, now we moving into failure strength, right? Failure strength. So what does this failure strength mean? Okay, this term is actually refers to the maximum stress of a material which it can handle before it breaks, right? So it's been measured in the megapascal or meganewton per meter square, right? Okay. For metal, we usually use something called uh, 0.2 offset yield strength, right? So this means we look at the point where the metal start to bend or where the metal start to deform permanently after being stretched or okay after we loaded in tensile or we squeeze, okay, we loaded in compressive, right? Okay, so metals is actually behaving the same way whether they are being pulled apart, okay, whether kita tarik, whether it is in a tensile load or even when we compress, okay, compress the specimen, okay. So that's making them reliable lah in the many situations, right? So same for tension and compression, right? How about polymer? Okay, like plastics, okay. Polymer, okay, for polymer, we identify a failure when the materials start to behave strangely, okay. Dia pelik sikit, they start to behave strangely. Usually it's about 1% of strain. So this means that after we stretch or we compress the plastic, okay, we compress a bit, okay, it does not return to its original shape, right? So what caused this change? First, we have shear yielding, okay. This is when the tiny change, okay, the tiny change, molecular change inside the plastic, okay, they are slip past each other, okay. So that's leading to permanent changes, okay. The second factor is crazing, right? Crazing here. So this happen when the tiny crack from inside the plastic, which can make it look white or look white lah. Kita nampak plastik tu becoming white. Sometimes when we bend, okay, there is a white region on the plastic part, right? So it reach the permanent deformation region. Okay. Okay. Apa lagi? Slightly stronger. Okay. So plastic can handle actually a bit more pressure when you give compression to them. Okay. When you push them. So as compared to when you pull them. Okay. Under tension. Okay. So how much stronger? Typically about 1.2 times stronger in compression as compared to tension. Okay. Okay. For ceramics here, okay, for material like ceramics, glass, okay, the strength depend on how you're going to load them. For example, intention, right? If you load them, okay, you have ceramic and glasses, and you load in tension loading, right? So so the strength when we pull them apart, okay, when we pull, okay, we tarik, okay, the materials is called the fracture strength, okay, because the material will fail due to fracture. And when we compress them, okay, we push the materials, right? Okay, the strength when the material break under this compression loading, known as crushing strength. Okay, and usually the crushing strength, okay, when we push is much higher as compared to the fracture strength. Okay, and some more for ceramic, we also have the flexural strength. Okay, this is the strength we measured when we bend the material. We bend the material, right? Okay, for ceramic, usually it can withstand more stress uh, when the when we bend. Okay, when we bend the material, it can withstand more stress if we compare to if we compare to the fracture strength. Okay, when we pull the part. Okay, how much stronger? Is about 1.3 times stronger in bending as compared to the tensile. All right. All right. Next, we have composite. Okay, like fiberglass, apa lagi? Carbon fiber. Okay. For composite materials, we also measure strength based on how much it deviated from normal elastic behavior. Okay. Usually using a standard offset of 0.5%. Right. Okay, so as we know, composite made with fibers, okay, like fiberglass, carbon, wood, or maybe a knauf, okay. Okay, okay, so this composite is usually 30% weaker in compression, right? Weaker in compression to about 30% as we if we compare to the tension. So why it happened? Because the fiber inside the material itself, it can buckle. Okay, it can buckle under the pressure. Okay. So what we can say here, the failure strength is a way to describe how much stress on different materials can handle before the material break. Okay, and the value of the failure strength, all right, is varies. Okay, it varies. Okay, it depends on the type of materials and also the loading, right? The type of loading. Right. Here we have another parameter, the flexural strength, or known as modulus of rupture. Okay. Okay. The unit is sigma flex. Okay. Okay, and unit is all usually in megapascal. So what does this equation means? Okay, so this flexural strength is defining as maximum surface stress in a band in a beam during uh, during a band failure, right? We bend the beam, right? Okay. Imagine you have a long, narrow beam made of ceramic. Okay. Okay. For example, we have here. Okay. Konon we have a ceramic rod. Okay. This rod made of ceramic. So when you try to bend, okay, we try to bend this beam, okay, we apply force, uh, okay, we apply force at the end, all right, okay, and push in the middle. The beam, okay, this beam will experience stress. So, this modulus or rupture of flexural strength is actually the maximum amount of stress, right, that the beam can handle before it breaks or before the beam fracture. Okay, fracture due to what force? Due to this bending force. Okay. Okay. Okay, so we have this beam, okay. When you apply a force, okay, this force to this beam, okay, okay, the materials, okay, this beam will bend, right? It will bend. Okay. This one is with you here. Okay. So the material will bend. So what happened? Okay, the material inside here, okay, the materials outside, okay, this part of material will be stretched, right? Will be stretched. And the material inside, okay, the material here, okay, at the inside, this one on the outer region, right? Outer part. Yang what happened to this material here? The material here will be compressed, right? Okay, so this modulus of rupture is actually representing the point, all right, the point at which the stress on the outer surface, okay, on this surface becoming big or becoming too great, because that will cause this beam to fail, right? Okay, since we are talking about ceramic, right? Ceramics are typically very strong, but the behavior of the ceramic is it is brittle. Okay, meaning that they can actually withstand or hold a lot of forces before it break. But however, once it reach their limit, okay, the modulus of rupture or flexural strength, right? Once they reach this value, okay, they can shatter, they can break suddenly. Okay, so this is why knowing this parameter, modulus of rupture for ceramic is important for the for us lah, for the engineer, for the designers when designing the structure or the product, right? Okay. Okay. Next, we have yield function. Okay. When a material is under different types of forces, okay, that are coming from multiple direction, okay, at the same time, right, we have materials, okay, the forces are coming from different direction, right, okay, at the same time, okay, this is where we call it experiencing multi-axial load, okay, the material and the loading is coming from different direction at the same time. So what happened? Okay, it does not break, okay, or it does not change in terms of shape in the same way, okay, as it being pulled or stretched in one direction. Okay, if we stretch the material in one direction, we can see how it will behave. Okay, there will be necking. Okay, there will be okay, the cross section in the middle will be smaller as we pull, but when the material we have multiple loads that coming into the materials, all right, at the same time, okay, when the material is experiencing multi-axial loads, the way the material breaks does not same as it been in tensile loading, right? So to predict how and also to predict when the material will start to yield. Okay, what does it mean by yield? Yield is the material is experiencing permanently deform, right? Okay, so to predict when the material will start to yield under this combined force, we usually use this these mathematical tools or equation that call uh, yield function, right? Yield function. So this yield function will help us to understand how the material strength, okay, especially in complex situation, relate to its strength when being stretched in a straightforward way. So it is actually a formula that gives us a clear picture of when and how the material might start to give up lah, under various combined stress. Okay, so we have here the von Mises yield function, right? Okay, von Mises is for metal, and we have here sigma 1, sigma 2, and sigma 3. Okay, all these this sigma is actually uh, principal stress, right? Principal stress. If you have, this is a material, all right? So you will have this one in the you see the perpendicular. This one is not perpendicular. This is a sigma 1, sigma 2, and sigma 3. Okay, so these are the principal stress. Okay. Okay. Okay, we will look how to use this yield function. Okay, we have here a metal pipe of radius r and wall thickness t that carries internal pressure P, right? The pressure generates a circumferential wall stress, okay, of sigma 1, PR over T, and also we have axial wall stress sigma 2 PR over 2T. What is T here? T is the thickness of the wall, right? At what pressure will the pipe first yield, right? Okay. Okay. To find this internal pressure, okay, we need to find this pressure. Okay, first we need to examine the stresses that been generated in the pipe open, right? So this internal pressure. Okay, so if you look at this, we have uh, two primary stresses, right? Sigma 1 and sigma 2. Okay, first, okay, we have a hoop stress or circumferential stress, okay. Okay, so this one, the sigma 1 equal to PR over T. Okay. And second, we have the axial stress. Okay. This axial stress. Sigma 2 PR over 2T. Okay. Okay. So the material is metal. So for metal, what are we going to use? We're going to use the von Mises yield function, right? Von Mises is for metal. Okay. So the von Mises stress, right? We need to calculate the von Mises stress based on this equation, right? The von Mises yield function for metal. So we have a sigma 1 squared plus, no, it's not plus, it's minus. Eraser. Eraser. And okay. Sigma 1 minus sigma 1 times sigma 2 plus sigma 2 squared. This be square root, right? Equal to, what is sigma 1? Sigma 1 is PR over T squared minus sigma 1 PR over T times PR over 2T. Okay, and plus sigma 2 squared, sigma 2 PR over 2T squared and square root, right? So then what do we want? We want the pressure. So we want to know all this P. Right? We want to know all this P. So what are we going to do? Okay. This one is actually should be equal to sigma yield of the material, right? Okay. When the pipe first yield, so it should be equal to sigma yield. Then you need to simplify this equation, all right? at the end you will get P, okay, pressure is equal to minus 2 square root of 3 sigma yield times the thickness over 3 r radius, right? Okay, so since the pressure cannot be in negative, so we convert to positive. Pressure sigma 2, oh no, it's not negative. Okay, 2 over 3 sigma yield times thickness over 3 radius, right? What does it means? It means that this pressure, right? This pressure uh, is where the pipe will begin to yield. Okay, is where the based on this pressure, right? This pressure is where the pipe begin to yield, right? That's where we calculate the von Mises stress is equal to sigma yield of the material, right? So this is how you're going to use the yield function, okay, to predict the failure of the materials, right? Okay. Okay. Next, we have sound wave that travel through solids, right? Sound wave. Okay, we know sound, okay, is a type of waves, okay. However, sound in the solids, okay, in a solid material, okay, it move as an elastic wave, right? So meaning that the particles in the solid, okay, will vibrate to transfer energy through the material, right? Okay, in a solid material, okay, sound often travel, okay, usually travel as longitudinal wave, okay, it travel in a longitudinal direction, okay, where the particle will vibrate in the same direction, okay, uh, okay, the same direction like how the wave is traveling in the materials, right? Okay, for example lah kan, you might want to imagine there are people in line, okay, orang beratur and they are passing the message quickly by whispering to each other. They want bisik-bisik, okay. So if people stand close together, okay, orang-orang ni berdiri berdekatan and they will respond quickly. The response will get quickly. So which means that the message move through the line becoming faster. Okay, kalau the people standing far from each other, okay, where contohnya is not less density lah kan. Bila the people are close together, the density is high. So if the people stand far from each other, okay, the response is becoming a bit late lah. So the message will move through the line becoming slower. Okay, So that's how you're going to relate between the sound and the density and stiffness of the material, right? So the longitudinal wave speed, okay, we have epsilon here, right? Epsilon can be calculated as a function of stiffness and density, right? So epsilon is square root of stiffness over density. So the speed of a wave depends on two main factors, stiffness and density. So it depends on the properties of the materials, right? Okay. Okay. Next, we have fatigue strength, right? Fatigue strength. Fatigue strength is actually the ability of a material to withstand or uh, to withstand repeated loading and unload cycle without failure. Right? So okay, if we look at here, okay. So if we look at here, okay, there is yes, any question? Okay, there is a specimen here, all right, the material here that that's been loaded. Okay, if you look at the loading profile here, we have the loading is going from minimum loading to maximum loading and go back to minimum loading, and it keep on repeated. The loading and unloading process is repeated, right? So these repeating stresses, right, will cause fatigue failure, right? Over the time, it will cause fatigue failure. Okay, when we have the material here, we load, we give tensile loading, and then we release, we unload. Okay, for several cycle, right? Several cycle. Okay, load, unload. This is one cycle, and it goes into several cycle. Right? At some point, it will experience the fatigue failure. Okay, materials have a specific stress level known as fatigue endurance limit here, right? So what happened below this limit? Okay, below this limit, the materials okay is able to handle high numbers of loading without breaking, right? So for examples, okay, if you look at these materials, the endurance limit that will cause the failure, okay, is 10 to the power of 7 cycle. Okay, it load and unload, load and unload up to 10 to the power of 7 cycles. Then it will encounter failure. So it the amplitude stress, if you look at this, it goes beyond the below the endurance limit. So that is where we identify the fatigue failure. So understanding fatigue strength is important to predict how materials will perform in real world applications, especially in structures and components that are experiencing cyclic loading. So as for example, if we have the wing, okay, if you look at the wing of this of of an aircraft, right? The wing is okay. The wing here, okay. The wing is always vibrating. Okay, it's always vibrating during the flight lah. It's always vibrating, if you can see. So this vibration, okay, this this loading and unloading, okay, will make the structure of the wing here is prone to fatigue failure, right? And next we have hardness. All right. Hardness is a measure of how resistant a material to deform, right? To deform, particularly permanent indentation, right? It is an approximate process to measure strength, and it is one of these non-destructive uh, method to measure the strength of material, right? So defined as the indental force divided by the area of the indent project normal to the direction of indentation. So what we can say here, from hardness, we will able to measure the material strength, okay, sigma F. This is the strength of a material, but the hardness value is actually 3 times of this material strength, okay, and the unit is megapascal, right? And we also have viscous hardness, right? For viscous hardness, where the unit is kilogram per millimeter squared, right? We can obtain, okay, based on this equation, okay? The hardness value, this H, divide by 10, right? So this is the viscous hardness test, right? We plan to do the test. Okay, I plan to conduct the lab session maybe next week, but based on the lab availability, I will check with the technician first, and then I will inform in the group, right? Okay. So okay, how to determine the strength from hardness, right? We have here steel. Steel has a hardness of 50 on the Rockwell C scale. Approximately, what is its viscous hardness and yield strength? Okay, so we know that steel hardness based on Rockwell C scale. So we look at this Rockwell C scale. So we make a line on 50 because it's given 50. So you want to know what is the viscous hardness and also what is the yield strength. So we go to the viscous scale. Okay, when we make this 50 line due to Rockwell scale, and we found that on the viscous hardness is about viscous hardness is about 500, okay, maybe 520, right? And the approximate yield strength is about 1,800 megapascal, right? So that is how we're going to determine the strength from the hardness value, right? Okay. And we have here toughness and fracture toughness. Okay. So these properties or this parameter, okay, toughness is given by G1C. The unit is kilojoule per meter squared, while fracture toughness is given by K1C, and the unit is megapascal meter 1/2, or mega Newton over meter 1/2, right? Okay, so what does this parameter do? So this parameter is actually measuring the resistance of materials to the propagation of the crack, right? If we look at this fracture toughness, okay, the fracture toughness is measured by loading a sample containing a purposely induced, okay, we purposely induce a sharp crack. Okay, we have a crack here. We purposely make this crack length of 2C, right? And then we load in tensile. Then we look at the tensile stress, okay, when this crack is propagated. So from that, we will able to determine this value of fracture toughness. Okay, is equal to y sigma times square root of pi c. What is y? Y is the geometric factor, okay, almost to 1, that depending on detail of the sample geometry. You might want to go into your textbook, and I believe there's a table showing the value of y for different geometry, right? So so for brittle materials, okay, this it will give us a clear and well-defined value for the fracture toughness. Okay, however, it's going to be a bit different for ductile materials, because ductile material will develop a plastic zone at the crack tip, which affected the fracture behavior, right? And for toughness, G1C, okay, G1C toughness, it measures the material's ability to absorb energy and deform before fracturing. Okay, deform plastically. It's not a permanent deformation, all right? It deform in a plastic manner before fracturing. So for G1C, we can obtain based on this equation, whereby we need the value of fracture toughness K1C divided by the modulus, and times Poisson ratio, right? Also same goes to the toughness, okay, for brittle materials like ceramics, glasses, it will have no problems, well defined, right? However, it exhibits significant plastic deformation in ductile materials such as metal, right? Okay. Okay. So this is how we're going to use fracture toughness, right? Okay. So to determine whether the glass floor panel, okay, we read the question first. A glass floor panel contain micro cracks up to 2 microns in length. glass glass has a fracture toughness of K1C 0.6 megapascals, okay, time meter half. When the panel is walked upon, when somebody walk on the panel, the stresses will be as high as 30 megapascals appeared in the floor panel, right? So you need to determine whether based on the given stresses in the floor panel, right? Is it the floor panel is safe? All right. So how are we going to do this? Okay. Okay. So to determine whether this floor panel, this glass floor panel is safe, okay, when given this specific condition, right? We can compare that. We can compare then to the applied stress, right? So, so for the applied stress, we should consider the critical stress for propagation. Okay. So, this critical stress we can calculate using this fracture toughness and also crack length, right? Okay. First, we list what been given. Okay, we have a fracture toughness. Fracture toughness K1C equal to 0.6 megapascal times M1/2, right? And we have the applied stress. This is the applied stress value. Sigma alpha is 30 megapascals. All right. And we have a length of micro cracks. Okay, this is 2C. Okay, micro crack is 2C, remember? 2C. Okay, 2C is 2 microns. 2 micron, which is equal to 2 times micron 10 to the power of minus 6 meter, right? So 1C, okay, just now 2C, 1C divided by 2, 1 to the minus 6 meter. So all in SI unit. Okay, now we can work the equation. All right. Okay, so the critical stress at which the crack will propagate. Okay, so we can calculate that critical stress based on equation K1C equal to sigma criticals over 5C, right? And we want to know the value of okay, this critical stress. We want to know this one. Okay, we know the value of fracture toughness. We know value of crack length pi. We know, so we can obtain the critical stress. So critical stress is equal to K1C over pi C, right? So K1C is 0.6 meter 1/2. Okay. Pi C pi times sorry. Pi times C, what is C? 10 to the power of minus 6, right? This one is 1.77 times 10 to the power of 3 meter. Okay, so divide by 1.77 times 10 to the meter. Okay, then to calculate, you will get this value 239.55 megapascal, right? And so this is the value of critical stress. So we need to compare with the applied stress to know whether it is safe or not, right? So since the applied stress is only 30 megapascal, okay, is okay, the critical stress is bigger than the applied stress. Therefore, it is the panel is safe, right? Okay, the applied stress is only 30 megapascal, but based on the calculation, the critical stress for this glass panel is 300, almost 340 megapascal, which is much more greater than the applied stress. So that is meaning that the panel is safe, right? So that's how we're going the fracture toughness to determine the whether the floor panel is safe or not, right? Okay. Right. So actually there are several more example that you can take a look in the textbook, right? Okay. So as a summary, okay, here there are 6 important families of material for mechanical design. Okay, what are they? They are metals, ceramics, glasses, polymer, elastomers, and hybrid materials. Okay, hybrid materials. What is hybrid material? They are combination of 2 or more material properties. Okay, so within a family, there is certain commonality. Okay, which means metal will have their own trait, ceramics will have their own traits, and etc. So ceramics and glasses, okay, they are hard, they are brittle and corrosion resistant, while metal are ductile, right? Metal are tough and good thermal and electrical conductors. While polymer light, okay, easy to shape and also becoming and good electrical insulators, penebat electric. We also have elastomers, Okay, elastomer can be stretched or sheared elastically to a large strain. It is this difference that make the classification useful. But in design, we wish to escape from the constraint of family and think instead of the material name and identifier for a certain property profile. Okay, so later we will compare among the properties. So by knowing all this, okay, it will guide you to make a material choice. Okay, we will continue on the material selection in the next week, inshallah, right? So so this is okay, this is the material properties or record of the properties for ABS, right? Okay, ABS materials. So if you look at this like a surat beranak lah of the material, we have general properties, right? General properties including density, price for this type of material, right? ABS material. And this record also have the mechanical properties. Okay, there are yang modulus, yield strength, tensile strength, elongation, the hardness, the fatigue limit, and also the fracture toughness. There are also other properties like thermal properties, electrical properties, and eco properties, right? So based on the properties, it has been used, this material, for several applications like safety helmet, camper tops, automotive instrument panels, and pipe fitting, okay, refrigerator, light linears, luggage shelves, and etc. Right? Okay. I think we stop now, and we will continue with exercises. Tomorrow, inshallah, we have several exercises to look into.